All right, thank you, Gary. All right, our next speaker is Curtis Roegner from the Northwest Fisheries Science Center. And Curtis will be talking about his method for quantifying the export of prey from wetlands to mainstem habitats, and importantly, why that matters. Right.
Good afternoon. I'm happy to be here to present some of these results and ideas. Let's see. Okay, so as part of the AEMR project, our conceptual model is that prey production in restored wetlands can benefit juvenile salmon without the salmon necessarily having to go into those wetlands. And we had kind of a large I'm going to tilt it this way. A multi-pronged approach to this idea. By studying salmon that actually do go into the tidal marsh areas, they benefit directly by going in there. Also by studying fish in the mainstem Columbia River, which are not necessarily going into these wetlands. And then my part is here, the flux of prey items produced in wetlands that get transported out into the mainstem and can be available for fish swimming by. So that's what I'm going to talk about today. So the outline here, we'll talk a little bit about how we developed a method for quantifying the transport of prey out, and secondly, to introduce a metric we're calling the salmon energy equivalence, which is a way of kind of looking at the importance of the energy that these insects have relative to salmon moving down. It's kind of a currency that we're thinking about using. And then I'll review some of the preliminary results. We looked at both reference and restoration wetlands. And then we'll explore some ideas we're coming up with trying to scale up from our individual wetland channels and sites up into the larger ecosystem. And then finally, some management implications. Okay, so first a little bit of math. It shouldn't be too bad. Basically, we're trying to find out over a given ebb tide how many insects, prey items come out of the wetlands. So from the top of the tide to the bottom. And to do that, we need to both measure the amount of water that comes out and the concentration of insects at these different time periods. We do that with a little ADCP for the currents and a Newston net for the insects. And we time these measurements so that we have the concentration coming out at the same time we have measurements of the velocity. And that's called the instantaneous transport, which comes out as individuals per second leaving the tidal creek. So here's some time series measurements that illustrate both the water discharge and the concentration. And you can see in this case, the water coming out of some of these tidal channels comes out pretty quick, a couple cubic meters per second over extended periods of time, then dropping down to zero as the tide goes down to the bottom of the ebb. Just as an idea of some of the volumes we're talking about, in this case, it's about 10 Olympic swimming pools of water that are coming out every single ebb tide. Secondly is the concentration, and here I have two examples of some of the organisms. Our chromatid midges, which, as we'll find out, are super important, and everything else. And just in this example, you can see that the midge concentrations over time don't really seem to vary. It's at the same concentration over time, whereas the other stuff varies quite a bit. And you can see that in this case, everything coming out is pretty much midges. And everything here is other stuff. And there's a lot of other stuff. Okay, so that's just the basic data we collect, and then some of the calculations shown here, instantaneous transport, insects or individuals per second coming out now, and you can see our numbers are getting pretty high in the beginning of the tide because all of that water is coming out at a fast rate, right? So 40, 60 individuals per second coming out of some of these tides. And then what we do then is like integrate over time, so now we're getting individuals every 5 minutes, and the numbers start going up, right? So finally, we integrate that over the whole tidal period to get our total numbers. So here's the integration, looks like that, and this is the total number of insects that, actually, total numbers of just the midges that came out in this tide. And that's a pretty big number. You start to think, really? Is that right? Well, it could be, for sure. If we had one individual per cubic meter and 1 meter per second, that's one individual per second coming out. In a half an hour, or in 1 hour, it's 3,600. Over the course of a 6-hour tide, you can start to really rack up numbers, and especially because both the concentration and the discharge are higher than one, much higher. So a lot of insects are getting exported out of here. And what is getting exported out? It is definitely mostly insects. We've got a lot of other things too. In fact, the diversity is really high, but by far, by numbers, the insects really take it away. Some of these other things are planktonic and not necessarily coming from the wetlands. They could be sloshing in and out with the tides. But a lot of these insects are definitely derived from the wetland system. So this is production from the wetlands that is being exported. Notably, other things we are not seeing in the flux, and that includes a lot of the amphipods, also known to be prey for the salmon. Basically, all the things here, salmon eat. They eat, they're very opportunistic. But what's coming out here are mostly insects, and what insects are they? It seems like there's only 4 groups that make up most of them, and that's our midges, sandflies, water bowmen, and aphids. Although these are numbers from all the other families, and you can see there's just a highly diverse assemblage coming out of the wetlands. Okay, so the next thing we want to do is say, okay, so all this stuff's coming out, how important is it for salmon? So we divide this metric we're calling the salmon energy equivalence, and basically what we're going to do is turn the amount of prey coming out into energy, kilojoules, and then divide that into the metabolism of the salmon. How much energy does a standard salmon, need in a day? And that ratio will be the salmon energy equivalence. So first, we need to know how many of the creatures are coming out. And so for the midges, this is the data we got from the interweb. It's about 10 to the third grams per individual, and their energy density is about 3.83 kilojoules per gram. It's about medium for a lot of the prey. So then we can sum all that up for all the insects, all the midges that were coming out, to get the total amount of energy, kilojoules, that come out in that ebb tide. And then for the salmon, we had to make some choices here, so we decided to take a standard salmon for a yearling. It's 180 millimeters, say. Its metabolism from the internet, again, is about 50 kilojoules per kilogram per day. And so when we do the math, we can get an idea that our standard salmon here needs about 3 kilojoules per day for a basal metabolism, not growing, not starving. So then by dividing basically 3 into the amount of energy coming out, we can say how many yearling salmon can be supported by the amount of insects coming out of the wetland. And just as a note, because subyearlings, our standard subyearling is only 80 millimeters, weighs less, and so you can actually, every time you see the numbers for the SCE, it's going to be a yearling, but if you want to know subyearlings, multiply by 12. Okay. So this is complicated a little bit, but I'm just going to show here, these are the different habitats that we looked at over time. So we had forested wetlands, emergent, and restoration, emergent wetlands. This is just some of the characteristics of those sites. Here are the C values for our different insect types, and then here's the total. And what you can just see for the total is that for the yearlings, we're getting something like 10 to 100 yearlings can be supported per tide for each of those different channels. And if you look at what insects that make it up, it's by far it's the midges. But in some cases, for instance, this forest site, we're getting a lot of other creatures coming out too. So it varied across the different sites, and it varied across the different habitat types. But essentially, for each tide, we're getting a significant number of salmon, yearling salmon, can be supported by the energy coming out. Okay, so now I'm going to wave my arms even more and just think about a little bit how we're going to try to scale up the information we're getting from these individual channels into the wider ecosystem. So, and we can do it over different ways. So first let's take scaling over time. So we just looked at some of the rates that we're getting here. For instance, this big stream can support about 800 or so salmon per day, and this little one about 100 when we do the scaling. And then, if you scale it up over time, you can get some large numbers of salmon could be supported over the course of, say, a month of June. So that's one way you want to try to look at the importance of these channels over time. Another way is by scaling up by the metrics of the channel. So since we can't sample them all, we're going to try to anticipate a channel of, say, this morphology, which looks similar to these ones. Maybe those rates are the same. So now we can scale up that way to get a larger picture of what's happening in one tidal wetland. And similarly, there's habitat differences. We looked at emergent, forested, and scrub. There's definitely different kinds of insects coming out. So when we add all those things up, they'll have different numbers of salmon that can be supported. Also, the restoration and reference trajectories. And a big one, of course, is the differences between the hydrogeomorphic reaches, because we're looking at Cathlamet Bay for most of our stuff, which has very high tidal fluxes. So that's what's really going to drive a lot of the stuff out. And further upriver, where it's more river dominated, that won't be the case. But here's an example of what we can do for, say, Carlson Island. There's really two habitat types here. It's the forested wetland and the emergent. So using the rates that we know of from these ones that we studied, we can apply them to other ones around, again, to try to build in what's the regional importance of these fluxes for salmon. And other factors that we need to consider, of course, the spring neap cycle. During big spring tides, more goes out. During neap tides, less goes out. Seasonal effects are really important, both for metabolism of the salmon and also the production of the insects, and all that can be worked into the modeling. And to just leave you with this one as a way of thinking about, we studied a few of these channels in these places. Finding significant numbers of salmon can probably be supported just from them. And of course, Cathlamet Bay is probably a gigantic production site for insects being exported out into the mainstem, where they can be used by fish that do not have to go into those wetlands. So when I'm talking about yearling salmon from upriver. So we think places like this are going to be hugely important for salmon, but anywhere you have wetland systems with a lot of these channels, you can expect they'll be exporting insects into the mainstem. So just in summary then, we so far have looked at 2 seasons, 11 different tidal channels. The transport is definitely dependent on the hydrography of each of these channels, so we really have to go out and study some of these a little bit more to really get an idea of how we can model them to places that we don't sample. So both the discharge and the production of insects are important. But so far, by far, it's these midges. They were everywhere. But based on just using the salmon energy equivalence idea, tens of hundreds of yearlings and literally thousands of sub-yearlings could probably be supported in single tides from all the stuff coming out. Management implications, well, these wetlands are distributing food into the mainland site. Migrating salmon from all the runs have to go right by Cathlamet Bay, so it could potentially benefit basically all the runs. The salmon, again, do not have to enter these wetlands in order to benefit from restoration projects. And so it's important to preserve the wetland food webs and also to continue to restore the degraded systems. Thank you.
Any questions for Curtis?
Great talk, thank you. I'm just curious, did you look at import of organisms on flood tide?
Not in this particular study. We have, not in this particular study, though we have done that in the past. In some places, there is definitely a flushing in. A lot of things come in, and it depends on the dispersion on the outside, whether they re-enter. We worked in Seal Slough, and in fact, a lot of stuff was just transferred back and forth. But out here, as whatever's produced from that wetland comes out, probably gets dispersed away from that particular mouth anyway and doesn't come back in. Stuff could come in from other sides though, so that is an issue that we haven't dealt with here. But we do think that most of the insects that we found are important are produced in those wetlands.
Thanks.
Yeah, excellent presentation. Thank you. What do we know or what do we not know about the distribution of total dissolved gas during high spill periods at Bonneville, when we may see 125% TDG in the tail race of Bonneville? And do we know anything about how that's distributed as you approach the estuary and the mixing? And if we do we know that if it has any impacts?
You're talking about dissolved oxygen down here? Actually, I don't know much about that, but we're quite far from the dam down here. The main thing that we found with our oxygen sensors around is that the oxygen content of almost all the waters we've tested is no problem for salmon at all. It's only in some of the backwaters and things where it can get low, and that's usually during the high temperature periods as well. So we've done many like CTD casts with oxygen sensors on them, and the water column is well mixed with oxygen, no problem.
I got a question. So you're collecting some really good data, and I can see where some of the energy is going. Have you thought about using EcoPath to see if there's any trophic level interactions?
If I could get it to run on my new computer, I would totally use it. It seems like you have to have an old computer on that, but I haven't yet, and I think that's a really good idea. I think our main drawback right now is that we really don't know about the energy density of a lot of these insects very well. I mean, there's a lot of different ones. They really haven't been measured, so that's a big if. And so, saying the midges are really important, and it's one reason is that because they're abundant. But one large beetle or something that comes off can equal many midges in terms of energy for salmon. And so even though when I showed you the abundance of different kinds of insects that are coming out, there are a lot of midges, but that doesn't necessarily mean they're the most important thing for some of these larger fish especially. So that's one thing we want to look into is more the energy density of the different insect types.
You just hit my question on the head, but I'll follow it up with, when you look at the phenology of the different critters that you're sampling, and then you look at the systems that you're sampling, for instance, on Carlson, you've got wooded effluent that's going to flow right through your emergent wetlands. Are you able to partition between the forested and the emergent wetlands as far as what type of prey are being produced where?
Well, that's a great point, because we would love to be able to use like map the vegetation on the different wetlands and help us expect what's going to come out of places that we can't sample that easily. For instance, we really actually expected a lot more tree dwelling things to come out of the forest, especially spiders and things like that. It didn't seem to be the case this year. I mean, we only had 2 years of sampling, but that was one drawback, actually. But we think there's got to be, there's insect and vegetation relationships that have been developed. So, certain bugs like certain kinds of vegetation. And those are things that are getting exported. So I would definitely expect there to be a close relation to that. But so far, I haven't been able to tease that out of the data. And maybe it's just because the midges overwhelm so much that we're kind of spending a lot of time on them.
Thank you.
I have another question. So basically, you calculate the carrying capacity based on number of individuals. So are you considering the size of the prey, or the biomass of the prey, or just the number of individuals?
No, you have to know the biomass of the prey too. Its individual weight in order to convert the energy density to a total number.
Okay.
So basically, numbers to weight to the values of kilograms per kilojoules per gram, and then you know how many kilojoules come out.
Okay, so and another thing is that, are you considering the temperature as well as, because the metabolism affected by the temperature?
I'm sorry, I couldn't
So metabolism is affected by temperature.
Oh, sure, yeah. So right. So we took a standard metabolic rate just to show, just to demonstrate the procedure essentially. But, the heat of the water is going to have a huge impact on in the metabolism of the fish. So early in springtime, the same amount of energy of insects coming out can supply more fish because their metabolism is lower. In late summer, where it's heated up and the metabolism is higher, they won't be, the same amount of insects will support less fish because they need more just to maintain that basal rate. So that's something that we can easily model in because we have all the temperatures and everything from all these sites. So that'll be interesting to see. It could very well be that the first fish that come down in the springtime really get a lot of great energy. By the time fish come down later, they need to eat more and more and more in order just to maintain level.
And the another question is, the carrying capacity is also affected by, we need to look the density dependent factors. Does not mean that if we have enough food, does not mean that we have lots of individuals of fish. So certainly we have a density dependent factor. Right. So maybe, we cannot say that this is the good habitat, so we'll expect the more individuals of salmon. But there is some sort of the density dependent issues.
Yeah.
So maybe we need to also think about that one.
Yeah, that's good. I mean, right now this is just as simple as I can make it to try to think about, how to move forward. But ideas like that for expanding the models out and trade-offs, we definitely need to consider those.
Yeah, thank you.
I think we have one last question.
Just to get back to that temperature issue, I was wondering if you sampled long enough through the entire season to actually detect, if you could just describe kind of qualitatively what was the impact on production rates, not salmon metabolism, but were you seeing a lot more insects during peak temperatures in the summer, for example, and what was kind of the order of magnitude range that you saw across your sites and seasonality?
I can't really quantify that directly right now, but we do see a trend for increasing numbers. The flux definitely increased as the summer went on, and more different diversity of insects came out. But I should mention that this is we did our study in 2016 and 2017. So 17 was a huge flood. We went out on all we thought were going to be the right tides, and there was water all over the place. So that may have cut down on some of the actual terrestrial part of the insect flux. I don't know. So that's one thing we have to tease out. We're still, the insect data is really huge, and so we're still working through a lot of those issues.